Good evening, everyone. I'm Carolyn Jacobs, GBH Education, speaking to you from my home in Southern Maine. We are recording, and we will send out the link to the recording along with a link to a very robust resource document and the link to the slides tomorrow in an email that comes from Zoom. And you are welcome and encouraged to share that with your colleagues, share any of the links. We're using Zoom Webinar as our platform, and that means that the presenters are on camera and have the mic, and it's reserved for them. Denise Olson, Director of Marketing, is in the chat, and she'll be posting links along the way. And both of the presenters, Debbie and Sean, will also be in the chat as they see fit and can manage that with presenting. We'll try to get to your questions in real time. Many of you submitted questions ahead of time, and we've also reserved time at the end for Q&A. So hopefully we'll be able to accommodate everybody. Next slide, please. GBH is the education department that I'm a part of, is within GBH, which is Boston's public media station, and the producer of many iconic series that you see on your local station in your own home state. So these are just some examples. Nova, of course, is near and dear to science teachers. We also create American Experience, produce it, Masterpiece, Frontline, and lots of programs for kids. Very proud of our work. Next slide, please. In the education department at GBH, we have been producing educational materials for pre-K to 12 for over 40 years. We create media resources and programs for both formal and informal settings, and we give everything away. There is no cost. In coordination with PBS, GBH has founded and manages the platform PBS Learning Media, which is public media's digital learning service with thousands of free standard aligned resources. Next slide, please. If you're not familiar with PBS Learning Media, please, we encourage you to visit the site. You are welcome to browse without creating an account or logging in, but we encourage you to do so. It takes about 30 seconds. You're just giving an email and a password and answering a few questions. Because if you are logged in, then you can make full advantage of you take full advantage of the service. You can download resources, you can share them, you can have your students create accounts and share their work, share resources through Google Classroom, create folders, et cetera, et cetera. So this platform that has thousands of resources for pre-K to 12 across the curriculum, but we are very strong in science. And one of the key features of the site are short video clips coupled with support materials to flesh out more of an activity in the classroom. So let's see. I want to make sure I didn't forget anything. Oh, yes. I wanted to just address the questions that you asked as part of your registration form. We had over 100 of them. And a common theme of the questions were, where do I find resources and how do I use them? And to be honest with you, that is the meat and potatoes of tonight. That's what we're going to be addressing. So I feel confident that your time is well spent and that you're going to leave with resources and strategy ideas of how to use them. Feel free to post other questions in the chat, of course. Sean, would you go to the next slide, please? Sean is the Director of STEM Curriculum and Instruction here at GBH Education. And Debbie is a middle and high school science teacher in Utah. And we have gotten to know Debbie pretty well over the years. She presented with us at an NSTA conference, and she also acted as a very important teacher advisor on a project called Bringing the Universe to America's Classrooms, a collaboration with NASA that you're going to learn more about as we proceed. So you're in for a good ride. Thank you for joining us again, and I'm going to turn it back over to Sean.
Thanks, Carolyn, and thanks to all of you for joining us this evening. We know it's a really busy time of year for you, so we really appreciate you giving us your time. Here for the agenda, we've already worked our way through a chunk of it. I've gone through our introductions of Debbie and myself, the introduction to PBS learning media. As a reminder, just about everything we talk about tonight can be found on PBS learning media, and it's free. And then first off, right after this, we're going to talk about phenomenon, the role in science instruction. Then we'll start showing you some resources as examples of different ways to engage your students with phenomena in your science instruction. After that, we'll have a wrap up and Q&A. And like Carolyn said, we'll try to answer questions in the chat in real time, but if we don't get to them, we will catch you later at the end. So really quickly, to get a feel for how you all use phenomena in your science instruction now. Like, when do you use phenomena? Why, how? And if you don't, that's okay. You can say you don't know, or this is just where we're trying to get everybody on the same page. Okay, so it looks like we have a lot of phenomena at the beginning, and to sort of introduce the topic and inspire kids. So that's great. But also other places in the unit. So, okay. So I'm going to keep going here and start talking about like why phenomena, because we hear that a lot now. And it has to do with basically the next generation science standards that we're kind of advocating for kind of a newer approach, a different approach to teaching science. So the traditional approach, which we all probably got when we were growing up, is learning science as a set of facts. We're learning stuff about a topic, stuff that's already known, kind of the truth. And instead, now, what the NGSS is advocating for is to more model science instruction on what scientists actually do. And what do? They're really working to help figure out and understand the world around us and the universe, how it works, why it's here. So that's the type of things that students should be doing in classroom. And so what they're trying to explain, those are phenomena. And they're trying to build a story or models that help explain something about each of these phenomena. So we're going from a learning about kind of model in the classroom to a figuring out something about a phenomenon. The difference of that might be, say you had a unit called particulate model of matter, molecules, but for this new type of phenomena-driven instruction, maybe it would be something like, how does the smell of popcorn travel from kitchen across the room to my room? So we have the phenomenon, something related to daily life. It's all the same content that kids would be learning, but it's just contextualized in a different way. So phenomena can be used in many ways throughout the curriculum. So the example we just gave about the smell and how it travels across the room, was an anchoring phenomenon. So it would probably be like the title of the unit. That's the driving question that throughout the unit, all the lessons and investigations are going to be working towards explaining that, developing a model to explain that. There's investigative phenomena, and the definition is kind of in the name, in that they do sort of the same thing, but at the lesson or investigation level. So they're just driving the investigations that as students are learning different aspects, different pieces of the model they're going to be putting together to answer and to figure out, explain something about that anchoring phenomenon. And then there are everyday phenomena. And those are things you can grab from the news, maybe something that's culturally relevant to your students and your community that relate to your instruction. So all of these together, you can see that phenomena play a big role in the, throughout the curriculum. So what makes a good phenomenon? Again, we want it to be able to drive instruction. And we want it to kind of guide and provide support for a coherent path towards the learning goal. So students are working to make a story, develop models to make that explanation. So therefore, it needs to be something that students can investigate and something that they can make sense of. Obviously, we want it to be interesting to the students. It doesn't have to be engaging as in fun and exciting. It just needs to be interesting, needs to make them wonder and elicit some curiosity so that they can derive some questions to investigate. Ideally, also, it's going to help make the content meaningful to students, whether it connects to their lives, to society, to their communities. Really, it's kind of why it matters to them. So it gives it more of a purpose for learning. There are a few common misconceptions about phenomena and their role in the science class. Again, a lot of times we think it has to be flashy and super exciting, but really it's more important for it to generate questions and guide some genuine inquiry for students. If students are interested in it.
Can I jump in there, Sean,
Of
real
course.
quick? Like why we're just thinking about this and maybe why you have ideas going on in your head about, okay, what would that kind of look like? And obviously we're going to give you lots of examples tonight. It could be as simple, and by not being flashy, it could be as simple as a ball that you have in your room and it bouncing on top of another ball and what that does in elastic motion. So it really doesn't have to be anything crazy. It could be something, objects that you have right there in your classroom. So I just want to point that out.
Right. And also there's the kind of corollary here. If students are interested in it, it would make a good phenomenon. Really, we want to make sure that phenomenon aligns with your instruction, aligns with your goals and the standards. So unless it does, and unless it supports that some coherent path to where you want to go, then it may not be ideal. So phenomena should be used just to provide the initial hook. So yes, that is one of the purposes for them to like really engage the kids into what they're going to learn, but it should be something that we come back to throughout the instruction because it's driving the instruction, and trying to learn about that and explain it is what the unit is going to be about. And it's going to help build coherence and help students build usable knowledge. And so likewise, people might sometimes think it's best to use phenomena after you've taught about the topic, and then just show them how it's useful. It's a fantastic thing to do, to show other situations and other phenomena that what they learned can apply to. But teaching these decontextual ideas often doesn't generate that usable knowledge that students can recruit and use in different situations. So again, we should be using the phenomena to drive instruction, but bring them in at different places as well for different purposes.
And I think adding on to that, if you give them the answers to that phenomena, or like explain it all within that time period that you're investigating it, the kids will lose interest, and you've just kind of, there was no point in that phenomenon in the first place. So you definitely don't want to give away all the answers. You want that curiosity and wondering to keep driving that interest and that engagement.
Okay, so I'm just going to show some examples from a unit. It's from the interactions curriculum that I was on the development team for several years ago. So the phenomenon is like static electricity, which is, in particular, how your clothes often stick together when they come out of the dryer. So that's our driving question, is why that happens. This is just the investigation of all the ideas that and questions that students are going to be working to understand, to develop a model so that they can answer this question. Here's some phenomena. These are the phenomena that are associated with each of the investigations. I'm not going to go through them all, but as you scan them, you can see that there's a lot of different types. There's the Van de Graaff generator, which is kind of flashy and cool, but we can't give those to all the kids. So they're using Scotch tape to develop a model to explain what they're seeing with the Van de Graaff generator. There's familiar things like the balloon rubbing against the shirt, sticking it to the wall, thunderstorms. So it's just a mixture of things that, not every single phenomenon is going to check every single box in what is a good phenomenon. But as you're, average it across the your unit, your curriculum, hopefully you'll have a mix and help make the content meaningful for your students. So how can media help? Because that's really what we're here to find out. The biggest thing is that it can just broaden the types and number of phenomena that you can have in your classroom, and makes everything more accessible, whether it's too slow, too fast, too big, too small. You can somehow bring those into the classroom. It also makes it more accessible to a broader number of students with closed captioning, video description. You can slow videos down. You can watch them over and over again, things you might not, which is an advantage sometimes from doing it in person. It just makes them accessible in a lot of different ways. In addition, media can really help you connect that science content to students' lives and society, which sometimes can be hard. And so this is can be a really useful tool for that. I think we want to emphasize that we can use media not just as an explanatory type of tool, but something where kids can actually engage in authentic practices. So they can make observations, to ask questions, look for evidence to support claims, interpret and analyze data, to look for patterns. So it really can support the 3D learning that is suggested by the NGSS. And then we also want to emphasize that we think media can't take the place of in-person and hands-on experiences. It's supposed to complement that type of science instruction and enrich it, but not be a complete substitute for it. Okay, so now we're going to get back, now that we've talked about phenomena and whether and their uses in the curriculum. We're going to go back to our activity here. And there were just so many good observations. I think there are a lot more people who know a lot more about this stuff than I do in this webinar. But this was just a very rich visualization, right? So you can see that people were focusing on a lot of different things. Some were about hurricanes, some were the motion of the wind, and then the large scale movements and the smaller scale movements and why that happened. Connecting it to weather and climate and just the movement of wind. So there are, there are a lot of connections you can make to the curriculum. Like I know I'm always drawn in by just the amazing amount of dust from the Saharan desert there in the bottom right-hand corner. And I think somebody else pointed out that up in British Columbia can see how the smoke is traveling. Those are wildfires, and you can see how the smoke is traveling and how far it's actually traveling. And that's something that we've been living with here pretty much east of Mississippi the last month or so. So that's what I was drawn to this time when I was looking at it. So these are the types of things that we can use to drive instruction. So this might be something to start from, and it could go in a lot of different ways depending on your curriculum. Okay, so while I said it's not necessary to use explosions, I'm going to start with explosions because I'm a chemist and, we like to explode things. And everybody likes that. So this particular resource is the structure of various molecules and the degree to which they explode and the energy with which they explode. So we have nitrocellulose, ammonium nitrate, and I think RDX. So very different amounts of energy there. So what could we do with a resource like this? Well, we could start with something like use it as an anchoring phenomenon. Like, why are some materials more explosive than others? And dig into things that would probably dig into something like the structure, how it relates to function, and how it relates to properties of matter. Could even go off after that as why explosions give off so much energy. Alternatively, you could go in, this is actually unit 2 of the interactions curriculum. And it seems to align really well with that 4th investigation. Where does the energy of an explosion come from? And so in this case, it would be maybe an investigative phenomenon. So there isn't necessarily a single answer for any given phenomenon where it belongs in your curriculum. It just depends how you're putting the ideas together, the goals you have for your students and your curriculum. As Debbie was saying, we can just use phenomena that we notice in the world around us. Things like that first question of socks that are stuck together, or how does a smell travel across the room? The Earth's phenomena related to the sun, earth, moon system are fit in that category. For all cultures, everybody looks up at the sky and wonders. And so these types of phenomena are just prime for investigating in the classroom. For the middle school standards, where the phenomena are like lunar phases, eclipses, and seasons. So we've developed a series of simulations to help students investigate these kinds of phenomena and kind of really understand this system. It's a Earth perspective on the top, and then the space perspective in the bottom. And you can play and go through the entire an entire lunar cycle and make those connections spatially between these two and start to explain phenomena. I'm going to digress for a moment because there were questions about how you use phenomena in classrooms for younger kids, for elementary kids. This is actually, you can find this in the Bringing the Universe to America's Classrooms collection in grades 3-5. And it was designed initially to answer questions like, why is a day 24 hours? And phenomena of how the sun and moon seem to rise in the east, move across the sky, and set in the west. So the difference there's no difference actually for the young kids and older kids. The only difference is the phenomena that you choose to focus on are going to have to be level appropriate, and the investigations you do are going to be probably, appropriate as well. So everything's the same, just for younger ones. So here's something that media can use, though, back to lunar phases. It requires a lot of spatial reasoning. So this is why it's middle school instead of this 3-5, because you have to really be able to picture what's going on from space and connect it to what you see on Earth. So here's this short video that you can see both Earth and the moon are half illuminated by the sun. And just this quick sweeping motion so that it's all happening in the same, can help kids make sense of and connect these two perspectives. We also have one for the full moon so that they could just start connecting these. And then the next level of simulation, the Earth view is simplified. We only have that, just the face of the moon in the, you see in the bottom left-hand corner, but we're quantitating that amount of illuminated side that's visible. So really honing in and trying to help them with that explanation so that they can picture it and explain the lunar phases. Okay, next thing could be, so how we engage students with phenomenon, it can matter. And media can help make it maybe a little bit more interesting and engaging for them. Debbie, are you talking?
Okay. Sorry, no, I was trying to find it. It's been a while for Zoom for me. Hi, everyone. Okay, I don't know about you guys, but as Sean has been talking and showing these resources, like my brain has been going a million miles per hour of like everything that I can be doing. So I hope you guys have a pen and a piece of paper and are jotting your ideas down as we go, because there's just a lot of good things that are coming up in between the lines too, as through this presentation. So I wanted to start off with this simulation that I've used a lot in my earth science class. And this is the North Atlantic, let's see, what's it called? Ocean circulation in the North Atlantic. And it's a whole interactive lesson. But what I love about these resources is that you can pick and choose as much as you want to and use them as driving phenomenon or anchoring phenomenon within your lesson. And so this is one of my most favorite, because just like the particulate one that Sean started with, this one is just visually like engaging. The kids are immediately drawn to this. And I've taught with this one for a few years now. This is one of the first lessons that was incorporated into this whole section on the site. And my imagery, different thoughts and ideas, just like you guys did as you were observing the starter tonight and looking at the particulates of so many different ideas. Oh, I hope that I'm not cutting out. My internet connection is being tricky. So this particular image, as you go down that checklist on the side, it addresses the entire DCI for this section, this particular NGSS. It's observable to students. And I think I'll talk about this on another one, but if you have visually impaired students, this is a great task to have those who aren't write beautiful descriptions and observations that help describe what's happening. And it really gets students to write better because they're writing for a purpose. They're writing for other students that need their help, and it can make all the difference. And it's definitely comprehensible to students once you point some things out, of course, because I use this with 8th and 9th graders, and they always have a little bit of trickiness deciding what this is actually showing because of the gray being the continental land masses. And so they always seem to struggle with that. So after I point that out, then there starts to be some more ahas and start to put some things together. But it is attention getting. It can keep students' attention. Just this video imagery can keep my students' attention for 30 minutes. They can sit and talk about it. Now, often I don't have that much time and I have to cut them off and be like, guys, let's figure this out. Let's get into more of this. But that's what I love about it, is it does get those kids excited and interested. And the last thing that I'm going to hit over and over again, you guys, with these resources is they are free. They are available 24/7. They are accessible on student computers. They're not usually blocked. And that's what makes these resources so great, whether you're teaching online, whether you're teaching in the classroom, whether you're teaching hybrid, these resources are accessible and easy to access. So that's kind of my plug with that. So how students engage in the phenomenon really does matter. And a lot of these resources that we share with you tonight are just visually compelling and get students to ask those questions that you guys started asking from the get-go tonight as we started this webinar.
So another example of how we engage kids with the phenomenon is just the basic changing levels of carbon dioxide in the atmosphere and global temperature. Highlighted the parts of the disciplinary core ideas that this addresses for both middle school and high school. So this is basically the standard way of showing the relationship between carbon dioxide levels and the global temperature. And we're starting from the late 1800s, because that's we're associating this with the Industrial Revolution. So this is a pretty kind of static traditional graph to look at. But what if we presented this data where the patterns emerged over time, sort of like it did for the scientists over decades, as they were identifying this pattern and knowing now that it's real and is going to have an effect. So we have a resource that does that, and we're going to see what it looks like in the classroom. So Tommy is the teacher. He's in a high school for students who are overaged and undercredited. So they might look a little bit older than your students. So while you're watching this, just throw in the chat what you notice about what's going on in the classroom. What do you like? What's really interesting?
Oh, what we're looking at is carbon dioxide over time, and the numbers on the right are telling you how high it's going. Oh, the dots are changing
over time, like more is being used.
Yeah, they'd add locations. Locations might stop being funded.
I have a question. That was always like fluctuating positively during January, the beginning of the year, but then it's decreasing in July, like every year.
That is the $1 million question. I love having student questions in class. It shows that they're listening and that they're thinking, and those conversations, can go anywhere. Can someone make an explanation for 1 year having a peak in CO2 and then a trough, a dip?
Because in the summertime, the plants thrive more
You're absolutely right. So say it in terms of CO2. In the summertime, the plants are growing. So CO2 is high or low?
Low,
Low. Why?
because they're eating up the CO2.
But what about the southern hemisphere? You know how it's like summer in Boston, it's winter in Brazil. What about that?
More land
More land where?
in the north.
So more land means more
Plants.
plants. The class was making connections in a really cool way. And I was able to sort of run with that in a way that as the teacher I hadn't planned. Wait till you see the ending. Buckle up.
Yo. What?
Okay, now watch.
Oh, it's gonna go down.
It's going backwards
Wow, that's crazy.
using something called the Keeling data. Keeling was a scientist. He was basically the first one to sort of ring the alarm bell of, hey, this is something we need to look at.
Wow, that's crazy.
So you're going back to the year 1200, 1000 and beyond.
What?
Going back further than that.
Remember,
It wasn't as bad as it is now, like it's drastically just going.
exactly.
Okay, so what did we see there? Well, first we saw a classroom that was really engaged in this data, this graph, as the data emerged. We also saw students that were driving the discussion, right? So it was the questions, their questions that were telling the class where it was going. And they were noticing patterns in the data as they're interpreting it. So this is really, multidimensional instruction in action. And another benefit of this was that the trend didn't come out right away. And so it wasn't presented to them as a fact. They constructed that as they were watching this data emerge and the pattern emerge. And that was the conclusion. The students came up with the conclusion, wow, it's a lot worse now than it ever has been. And so, so that is the goal, for the students to be constructing their knowledge as opposed to us just transferring it to them. So somebody had posted a question beforehand about how to fit this into your in your science teaching, because you're already so busy and the curriculum is full. Really, it can fit in just the way you normally teach, and it shouldn't take that much longer. If you recall the question that student asked about those dips and valleys in the pattern going up, Tommy could have just put a pin in that, posted it on the driving question board or somewhere, and then come back to it on another day, and then gone through a lesson using this kind of data. This model has a atmospheric CO2 and surface vegetation, and could go through several years and see the patterns of the season. So he could have had the students go through and collect the evidence themselves to come to that conclusion. But instead, he chose to do this all in like one period and maybe half a period. So a lot of this is up to you, and how in depth you have time to go and want to go on any particular topic or standard.
Okay, sorry, there's always a bit of a delay. This one, I don't know about you guys, but I love that video of Tommy's classroom. It just is like, it gets me excited to be back in the classroom. This week, I actually started back, and it makes all the difference to have your students there with their curiosity and their wondering. And so I just feel so energized looking at these resources again, and excited to just start teaching these things and hearing what my students come up with. So this one that I wanted to share with you is these resources that you can find on these that we're sharing with you are just so visually compelling, but there's a lot of components to them too. And so I chose this one because this one goes with an earth science one as well. Use a model to describe how variations in the flow of energy into and out of our systems result in changes in climate. but this specific lesson is focusing on a separate component of that can kind of drive this instruction, and it's mountains and rain shadows. And so what I wanted to point out with this resource, and I'll put this in there, is that you can pull, whether it's, you'll see on one side of the slide, there's a graph showing the difference on one side in Packwood, Washington versus Yakima, Washington. And so the graph is showing the amount of rainfall throughout the year. You could just pull those graphs and post those up and ask students to wonder, what do they notice about it? What do they wonder about it? You could pull just the image itself that is on this slide without the data, and have students question and wonder about it. And I guess my point being that when you introduce a phenomenon, it, like we said at the beginning, it doesn't have to be something flashy. It doesn't have to be something crazy or hands-on, or, I mean, it's always nice when it is, but it doesn't have to be. And no teacher in the world has time for that. It's not possible. And so to be able to go to these resources and find these beautiful images, these graphs, and I want to point out this graph, you know, this is, if you're a climatologist and you're looking at this graph, you know that this graphs are not this simple, right? And so one thing that is nice about this data is that it has been smoothed, and it's been smoothed, not too simplified. It's not simplified by any means, but it's been smooth. So it's a little more easy, especially for middle school grades, to maybe pick out patterns in the data. And, you know, that's one of the competencies of things that we're trying to get our students to do, is just the being able to look for those patterns and to make meaning of them. And that can be used as a phenomenon to make that. So again, the last check mark on this, guys, it's free, it's available. Your students can access it. You can access it. You can take that picture off of it. All of these resources are just there waiting to be used. And sometimes it's, for me, I don't have all of these things bookmarked necessarily. And so in a Google search engine, it's an easy search. I just type in, usually bringing the universe to America's classrooms. I'll just type that in, and then I'll type the topic that I'm looking for, and it'll pull something up for me, imaging, videos, pictures, something that I really can use in my classroom. So that's kind of my tip for finding those resources. And I'm sorry about my links that I posted, because they do say Utah on them. So we'll get you the right links that are not having the Utah. Obviously, that's where I'm based out of. So we'll get those posted.
For the most part, they should work. It's just a little slower because it has to go through something. I'm not sure about Pakistan though. So we'll work on it. Okay, so phenomena can also just help makes the science content meaningful to students, and kind of give that, why are we learning this type of contribution. One thing that you're all probably, regardless of what you teach, are going to have to maybe deal with this year is eclipses. This fall, there'll be an annular eclipse in October, and in out west and in east of the Mississippi, there'll be a full solar eclipse in April. So we have tons of resources, some really short. That second one of why, you know, everything is just set up just right in size and distance for us to have eclipses. If you have time, you can dig in and go through one of the ones on the right, and spend a class period or two digging in, like why are these so rare? Why do they only happen every once in a while? So can tackle something that's in the news. This is something that's very rare on PBS Learning Media. Most of the resources on there are supplementary. So they're meant to just fit into your curriculum wherever you need it to be enriched. This happens to be an actual unit. It's a 3-week unit, but you can also pick and choose what you do and do it in a few days as well. But just wanted to use this to kind of give you a feel for how the thinking behind creating one of these. So the phenomenon for this is nutrient pollution. So this isn't a normal, the usual engineering experience. This is environmental engineering. So they're going to be dealing with a complex problem. And nutrient pollution is just excess nitrogen and phosphorus in a body of water. And about 50% of our lakes and rivers have elevated levels of nutrients. So this is a problem that will likely be local and be affecting something nearby that the kids can relate to. This is also what causes that dead zone that you hear about all the time in the Gulf of Mexico. So the problem they're solving is they're going to try to develop a plan to manage nutrient pollution in the watershed. Excuse me. So why nutrient pollution? It was a meaningful problem because it's widespread. It's really important to society, likely could affect the community. There might be a pond that they can't swim in or they can't fish in. Excuse me. And also we designed this so that they could use ideas that they learned in science class. So they're applying things they learned about the water cycle, how water travels through a watershed, the carbon cycle. And so it's giving meaning to stuff that they've learned in science, and they're applying it to this meaningful problem. And it was also, since it's a complex problem, there's lots of stuff to investigate. I mean, just to define the problem and prepare to solve the problem. So how bad is it? They have to dig into big data sets so that they can find the data for their community and characterize the problem. Where did the nutrients come from? That's another kind of research. And tracking how nutrients move through the watershed. They're investigating variables of runoff and infiltration. So they want to minimize one and maximize the other. So, so it supports a lot of deep investigation. So that's just another example of how to think about introducing these phenomena when you're designing something.
Every time you talked about that before when we were preparing for this, it made me want to get in a class just to teach that specific project. Oh, it gets me so excited. Okay, now this is kind of a jump going from the engineering capstone environmental engineering. But remember the theme under this slide is making science content meaningful to students. So if there's something that most students can identify with or want to identify with, that is their phones, their cell phones, and how much they are on them. And so I wanted to point out kind of a different resource, maybe more on the computer science side, which a lot of schools and districts are heading in that way to provide more computer science opportunities. And of course, these web resources also provide helpful things in that regard as well. And I know that a lot of state core curriculum are incorporating types of computer science and coding as well. So I wanted to point this one out because one of the physical science in the NGSS standards is that information can be digitized in this form. It can be stored reliably, oh, I can't talk, it's been a long week, in computer memory and sent over long distances as a series of wave pulses. And so you can see this is a very simple simulation that's kind of an interactive that's on the website. And students can actually create their own images and flip tiles back and forth. But I could see using this with my students this year as we talk about looking at how information is digitized and putting up this image of the duck and then the codes to the side of it, and just having them just really quickly. High school students, it's probably not going to take very long for them to understand. Most of them have been introduced in some way to decode this, or better yet, to have them maybe decode the picture or draw the picture. There's a lot of different ways you could use this. But it's observable to students. It's something that is also meaningful to them. They're likely to comprehend it. A lot of students have a little bit of background in some way or another in talking about coding and computer science in the younger grades. And probably the kicker to this one, if you want to go to the next slide, Sean, is really letting them understand how resolution works, why their cell phone works in the way that it does and portrays the images that it does, or why a telescope can capture so much information and send it back to us in the earth science classes, but some images are going to be much more pixely than others, and why that happens. And so I love this because on the same interactive simulation, it shows a 4x4 versus an 8x8 bases versus a 16x16, and the difference in the imaging that comes from that. So a lot of these resources can have interactive simulations that are very usable to kids, to get them, especially those kids that want to be doing something, they will want to fidget with this and mess with it and make images and share it with their neighbors and their desk partners. And so this is a good way to get that conversation started, to get that interest in why do we see image resolution the way that we do, or how is that information digitized? And then you can get into discussions of standard definition, high definition, and the differences between that. But this is something that a lot of kids would be interested. They care about it. They are constantly storing and taking digitized information. And so this is a good topic that a lot of people don't realize is available on the site. It's not just earth science things. It's not just beautiful satellite imagery. There's a whole bunch of different resources out there.
And just going to go through some of these really quickly. These are just some examples in the Beyond the Elements collection. There's this polar and non-polar molecules interactions resource, and there we're looking at a micelle. So how does soap work? And which is something that we do and need every day. There's so many cool and kind of controversial things that are happening as far as with molecular biology and like gene therapy, CRISPR. I have another resource on the DNA testing for genes, for the breast cancer genes. And this company only tests for 3 of like 12. And so people can sometimes get a false sense of security and make perhaps not the ideal health choices. So these are all kinds of things that make it why it's important to understand genes and molecular biology, because these are the kinds of decisions that as citizens, they're going to be making as they grow up. And in the middle here is the, it's an impacts of a mega drought on the Amazon rainforest. When I first saw this image, I thought it was somebody kayaking around in the Arctic. But if you look a little closer, the guy is fully geared up. He can't breathe the air. He can't touch the water because it's just so dangerous and poisonous. It's actually foam that he's paddling around in, and it's foam from waste. It's phosphates from waste that factories have dumped into this river, and the flow of the river isn't enough to wash it all the waste out into the ocean because of the mega drought in the Amazon rainforest. So just this image, or you could use the whole video, and it could set off discussion or about systems, what happens when you change one thing in a system. It affects a lot of things downstream. Or just human impacts on the environment. Okay. And then, of course, if you don't know what will engage your kids, then just talk to your students.
That's for sure. I think that's one of the best pieces of advice I could give any teacher if you're trying to figure out like what is a phenomenon that my students would be interested in. Talk to them. One of the things that my students do living here in Utah is fishing. I have a lot of outdoor students that just love fishing. And so when we were talking about light wave or transmission, and the next slide too, I'll show you a picture, but we talked about how does the color of fishing lures affect how well you're going to catch those fish. And so there's this video on the collection that's Colors Underwater. And I love this because this is something that you wouldn't be able to do in the classroom because you can't take your students down 155 feet in the water. And so this is something that allows them to observe. It's visually stimulating. They get an idea for what it is, and it takes them down and shows them the color differences as we go. So just like in Tommy's video, as he was teaching, showing them in real time, you can take a real time trip down to the bottom of 155 feet, watching the colors change on those little pipes that they take down there. And then because of that, it led to all these great discussions of the colors of fishing lures. You could expand this out to letting them design and create their own, and engineering standards, in testing them out, in doing more watershed studies and looking at the depths of the lakes around you. And it led to students wanting to test out their own. And so it's just, these resources can be as simple as a picture, a video, a discussion that gets students sparked in thinking about what does this really mean, and engaged in wanting to drive that instruction to learn more about it. I love it. And we're getting close out of time, so I apologize. Sean has so much more.
How far are we? Oh, okay. I should probably, okay. We'll just try to go really quickly. So investigating phenomena that are inaccessible to the classroom. This again was a question posted beforehand. So we'll just give a couple examples of how to do that. So for the how Earth's surface changes over time, that's a big time scale. How are we going to investigate that? We have this resource where students can virtually visit several sites across North America. These are gigapan images. So that means that there's dozens, maybe hundreds of high resolution images all stitched together to make this. And so you can see the whole landscape, but then you can also zoom in almost to the individual rock stage, and up there at the left in the upper left hand corner, that yellow square tells you where you are. So you can use this to explore, investigate a lot of things. The example I have here is evidence of erosion and weathering, but it could also be used for traveling up and down the eras within the up and down time within the Grand Canyon, and characterizing the rocks and looking for evidence there. You can also choose to use resources. A lot of the NOVA videos that we have scientists talking about evidence and how not just about things, but the evidence that supports their claims and why it supports their claims. So they're modeling those claims, evidence, and reasoning that that are often difficult for students, as well as just showing students how to think critically about the evidence and how we know something happened. So to dig even deeper into sometimes esoteric kind of topics, we can maybe focus on not just what happened, but how do we know? So put that focus on the evidence. So things like the Big Bang Theory, and it's supported by redshifts and galaxies that are moving away from us. So what if we let kids actually collect the evidence themselves? So we developed this resource in collaboration with Worldwide Telescope, and it gives them access to real data that scientists use. Up in the left-hand corner is a basic map of the known universe. So some of it is known more than others. The blue dots are individual galaxies, and by clicking on them, can go and actually visit it. then by taking a little, they can estimate in a really rough way the distance, and then click into get the actual spectrum of the galaxy. And they can look at the redshift and then make a graph and calculate Hubble's constant themselves. So they're at least focusing on the evidence and kind of gathering it and measuring some of these important ideas themselves. Likewise, how did Earth form? Right there in the DCI, it says that evidence has been destroyed by geological processes of what happened in early Earth. So how do we know? Where did this model come from? So again, we have a resource that gives you a timeline of the best model that we have for what happened in early Earth. There's the line of events, but associated with that is the evidence for that. So how do we know? And this is also ripe for nature of science discussion, because even while we were making this, the models were changing because there is so little evidence that just a couple new pieces can really change the model significantly. So it makes it ripe for that type of discussion as well. So sorry, I've gone kind of late. This is just a reminder that just about everything we've seen is you can find it on pbslearningmedia.org, and it's all free. You'll be getting everything in a list with links that you can go to. These are collections that you might want to check out of various topics. Check out some of these, even though the addiction in cannabis, they have some standard biology of things like homeostasis, feedback, and signals in the brain as that are contextualized around these issues. Now I'm turning it back to Carolyn.
Oh, you're muted, Carolyn.
Yeah, I just saw my red microphone on the camera. Thank you, Sean and Debbie. I think I wanted to bring up a couple of points that are assumed by us because we know them so well, but we may not have made explicit to you. And that is a lot of the resources on PBS Learning Media, some of which you saw tonight, are short video clips. And so if we're drawing from a NOVA program, we're not playing the whole NOVA program. We have carefully edited a clip, typically 3 to 5 minutes, that stands alone, addresses a standard, and also tells a story and fits the standard. So the other thing is we use the word collection. You just saw a few banners of different collections of resources on PBS Learning Media. And a collection in our world is one URL that takes you to a page on PBS Learning Media that includes many links to resources within that collection, organized around a theme or a topic or whatever. So, and when you go into the site, if you are, one wonderful way to start searching the site is to search by collection. You can filter your search by collection and then start there. And when you go to the page, you can save to your folder the entire collection, or you can save individual resources. More on that at another time, I guess. All right, so this is the survey, our post-webinar survey that our research department manages. It's anonymous. We really appreciate you taking the time to do it. We listen carefully to your feedback. You do have an opportunity in the survey to give us ideas of other topics that you want to see on webinars, and also to express an interest in being a presenter, just like Debbie is tonight. After completing the survey, you're welcome to download a certificate of attendance, and we give you a couple of weeks to do that. And for those of you who are watching this as a recording, you may also complete the survey and download a certificate by watching the recording. And the last slide, please. I think I have, yeah. So these are links that you're going to get tomorrow in this follow-up email. The slide deck from tonight, the resource document with links to everything you saw tonight, plus an awful lot more. The post-webinar survey, and of course, we encourage you, if you're not already, to sign up on our newsletter site so that you make sure that you get notice of other things that are coming up. And that's my contact information, Carolyn_Jacobs@wgbh.org. I will get you to the right person if you email me any comments or questions, and we really appreciate your time.